Okay, in this video we're going to talk about graphs of polynomials, and there's two different points of view that we have with graphs of polynomials. One is thinking about looking at the graph of the polynomial up really closely, where we can see all of its little wiggles and gyrations. And then the other point of view is the 30,000 foot view, where we think about what the polynomial looks like from way, way, way back, where the wiggles in the middle are not as visible in the scale. So first we're going to talk about that high view, that long range view. And when we do this, you'll see this notation used that I've circled on here. You'll see this X arrow with the infinity symbol and X arrow with the minus infinity symbol. We can think of that as, just imagine on a number line, and we think of positive infinity as going to the right and negative infinity as going to the left. So big positive numbers will be to the right, giant, very negative numbers will go to the left on a number line. So that's what we mean when we write X arrow infinity or X arrow minus infinity. Just on the graph, go to the right or go to the left. We're using this notation because this notation is common in calculus, and so I want you to get used to looking at it, but we can just think of it as going to the right or going to the left. So the question here is, as your graph goes to the left or right, are the Y values going up or down? That's the entire purpose of this whole first video. One way we can see that is, remember, we can, anytime we have a function like the one we have here, we can give ourselves a few points to plot. And so if I want to know what's happening as you go to the right, then I can pick a big number out to the right. So something like 100 is a fairly large number going out to the right. If you figure out what that is, so f of 100 in this formula will be minus 2 times 100 squared, which is minus 20,000. You can put that in your calculator if you don't believe that. That is very, very negative. So if I were to plot that as a point, the x-coordinate would be 100, which would be way out on the right-hand side of my graph, and the y-coordinate would be negative 20,000, which is really, really, really far down. So let's compare that to what happens when we put a big negative number in. So this is an x that's way out to the left of the middle, and then f of negative 100. If you check it, you'll get the same calculation, and the reason that happens is because minus 100 squared is also 10,000. A minus times minus is positive. And so if you go out to the left, then your y-coordinates also go way, way, way down. And so a very rough sketch of that would look like this, where I know that I have my axis. If I go way out here to 100, my y's are way down there at minus 20,000. And if I go out here to the left to minus 100, my y's are also down here to minus 20,000. So what I'm seeing is that I think that as the x goes out to the right, the y's are going down. And I can say down in the y direction by saying arrow minus infinity. And as x goes out to the left, y also goes down to minus infinity. So this is the way we can say it in a very mathematical way that you'll pick up on in your calculus class. But for all intents and purposes, you could also say this as x goes to the right, the y's are going down. As x goes out to the left, the y's are also going down. And so just FYI, the real picture for this is here. This is the real graph of that function, and we can see the behavior that we talked about. As your x's are going to the left, your y's are going down, and as your x's are going to the right, your y's are also going down. Okay, so we could play that same game with this second one. Erase a little bit of that so I can see it. Here the function is g of x equals 3x cubed, and so I can play the same game of just putting in a couple of numbers, maybe even 100 and negative 100 again, thinking of those as being x's that are far out in each direction. And what we should see as x goes out to the right, the y's are going up in this case. If you were to use, if you use x equals 100 as your sample point, the y coordinate for that is going to be 3 million. So very, very big positive number. As your x's go out to the left, so out past a number like x equals negative 100, then your y coordinates are going to be really, really negative. If you put negative 100 in here for x, you're going to get negative 3 million. So I encourage you to try it on your calculator, but that's what you should see. And then, just like before, we can look at a real graph of this and see that that is in fact what's happening. As the x's go out to the right, the y's are going up, and as the x's go out to the left, the y's are going down. That's all that's saying. So we have fancy notation for something that's a very visual concept. Okay, so why do we do that? Well, we do that because that is something we have to pick up on a little later as part of the analysis of more complicated functions. But for now, one benefit that it has for us is, well, hang on, let me just rearrange this. All right. Right now it helps us raise an interesting point about polynomials that is important later on, and that is when we have a complicated polynomial like the ones that you see here where there are multiple terms, these behave like their their leading term. So they behave like their highest degree term. So if I zoom out, if I zoom far out where I'm looking at this 30,000 point view, then the only term that really matters here is the highest degree term. And so similarly, this would say, looks like y equals 5x to the fourth, again, from really, really far zoomed out. And what I'm doing there is I'm just looking for the highest degree term in the polynomial. So what do I mean by looks like? Well, I have some pictures here to show you. The graph of f of x equals 3x squared minus 6x plus 1, I'm saying from far enough away, it looks like just y equals 3x squared. That's its highest degree term. And I'm saying that this polynomial looks like y equals minus 2x cubed, since that's its highest term. And again, when I say looks like here, I mean not in the middle, not where all the wiggling happens, but out, far out at the ends, like we were seeing in the previous pictures. So let me just show you the pictures of these things, so you can see what I'm talking about. In each case, the blue curve is the original. So the blue curve is the original function, and the yellow curve is the one I'm saying that it looks like. Notice how zoomed out my scale is here, that I'm looking at this from far away. My y-axis is in the hundreds going up. And so when I say it looks like it, I mean it's following the same growth. So whichever way 3x squared is going, up or down, that's what the overall polynomial is doing. And there'll be an exception to that. I'm totally ignoring what's going on in here. The two graphs really don't look the same in that middle area, and we don't expect them to. Same in here. So these middle areas, the graphs do not look the same, but out here at the ends, the graphs are going in the same direction. In fact, they're very close to each other as they go out. And so that's what we mean when we say these things look like their highest degree term. The advantage to us here is that if we wanted to know what the graph is doing as you go out to the right or go out to the left, then it's definitely easier to do that analysis with the simpler curve. Right? Doing that analysis with this is simpler than doing it with the original, and doing that analysis with this is simpler than the original. Not that you can't use the original, but we can take advantage of the fact that these are similar by just substituting the largest term in that analysis. But again, that behavior as you're going out to infinity in either direction, that is a zoomed out big picture behavior. That is not going to help us at all understand what's happening inside of in the middle where all the wiggliness happens for polynomials. And so we'll talk about that next.